Have you ever wondered why even the sharpest images have this inescapable blur? Let's get into it.
You know, we have these incredible telescopes, but there's a hard limit to the details they can actually resolve.
And it's not a flaw in the gear, it's actually a fundamental property of light itself.
That property is called Fraunhofer Diffraction. It's how distant light waves bend as they pass through an opening.
We're focused on Fraunhofer because it deals with distant, parallel light waves. Fresnel? That's a whole other story. So, since light acts like a wave, it doesn't just go straight through a slit. It spreads out. And here's the wild part. The smaller you make that opening, the more the light actually spreads out.
This spreading is just unavoidable. Think about a laser pointer. That beam has to get wider over a distance. Okay, so that's a slit. But what about a circular lens, like in a camera or a telescope? Well, a star doesn't show up as a perfect point. It's this blurry spot called an Airy disk. Now, things get really interesting when you try to look at two objects that are super close together.
The Rayleigh criterion is the rule of thumb that tells us when we can see those two objects as separate.
So how does this limit our real-world gear? Let's see how it works with a pair of binoculars.
For a pretty standard 35mm lens, the absolute smallest angle you can possibly resolve is, well, it's tiny.
So for stars 30,000 light-years out, they'd have to be over half a light-year apart to be seen as two.
And hey, this isn't just for telescopes. It limits microscopes and even your own eyes.
This is exactly why scientists use things like UV or X-rays. Shorter wavelengths can see smaller stuff. So if this blur limits everything we see, from the cosmic to the microscopic, what are we missing?